Welcome to Part 8 of the CipherVibe Cloud Security Capabilities series. This episode explains integrations and ecosystem, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. Security integrations move evidence and decisions across cloud providers, scanners, ticketing, messaging, identity, data, and response systems. A reliable ecosystem depends on stable contracts, least privilege connectivity, ownership, observability, and clear authority over each record. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand integrations and ecosystem, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, inbound connectors collect assets, findings, identities, events, and business metadata using APIs, streams, files, agents, or webhooks. Second, outbound integrations create tickets, notifications, pull requests, response actions, reports, and data lake records. Third, canonical schemas allow tools to exchange common fields while retaining source-specific evidence and identifiers. Fourth, integration governance covers credentials, scopes, rate limits, retries, ordering, duplication, retention, and decommissioning. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for integrations and ecosystem follows a repeatable evidence lifecycle. First, define the business decision and integration supports before selecting fields or authentication methods. Second, map source and destination ownership, identifiers, status models, update direction, and conflict resolution. Third, use scoped service identities, secret rotation, validation, idempotency, correlation identifiers, and replay protection. Fourth, monitor freshness, failures, lag, rate limiting, schema drift, duplicate creation, and authorization errors. Fifth, test upgrades and failure modes, document recovery, and remove credentials when an integration is retired. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate integrations and ecosystem is to study how the capability can fail. First, bidirectional synchronization creates loops or overwrites authoritative status when ownership is unclear. Second, broad integration tokens provide an attacker with cross-system reach and sensitive data access. Third, silent schema changes drop fields or misclassify findings without obvious connector failure. Fourth, webhook retries and out-of-order delivery create duplicate actions or regress workflow state. Fifth, a large catalog of unowned integrations becomes an invisible operational dependency. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable integrations and ecosystem program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, publish supported contracts, version schemas, validate payloads, and preserve source provenance. Second, use per-integration identities, minimal scopes, short-lived credentials, network restrictions, and rotation. Third, design idempotent consumers with deduplication, ordering strategy, retries, and dead-letter queues. Fourth, expose connector health, freshness, permissions, throughput, latency, and last successful synchronization. Fifth, maintain owners, service objectives, test environments, change notices, and decommission checklists. Control design should include preventive, detective, responsive, and recovery layers. Together, they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for integrations and ecosystem should build trust before scale. First, begin with authoritative asset, identity, ownership, and ticketing systems. Second, standardize authentication and health telemetry before adding a large connector catalog. Third, create reusable mapping, retry, audit, and secret management components. Fourth, add response integrations only after approval, rollback, and verification are defined. Fifth, review business value and retire integrations that create maintenance cost without improving decisions. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include connector freshness, integration failure rate, duplicate action rate, credential scope violations, and time to restore synchronization. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.